Okay, class. Today let's start chapter 10 of the textbook. This is the last chapter we're going to cover this semester. Okay. Chapter 10 is flow in conduit, pipe flow. Okay, it's a very important topic. Before we talk about the pipe flow, a couple of things we want to emphasize here. The first thing is the Reynolds number. Okay, I think I mentioned this in the beginning of the semester. Reynolds number is very important. We use the number to, it's a dimensionless number. We use it to characterize the flow, okay? Reynolds number, the equation is this. There's the different forms depending on what you have, okay? Reynolds number equal to velocity. V is the velocity times the diameter. Okay, D is the length scale. In this case, in the pipe flow, it's the diameter. Then divided by the viscosity, kinematic viscosity. Okay, so if you use kinematic viscosity, is Vd over nu. Okay, if you use dynamic viscosity, second the form is rho Vd over mu. Okay, depending on which one you have. Okay, either way. Velocity is flow rate divided by cross-sectional area. Okay, so if you are given volumetric flow rate or mass flow rate, it will be these two forms. Okay, because velocity equal to q divided by quarter pi d square. Okay, one d is cancelled by the d in the numerator, so it will be q divided by pi d. Okay, then 4 times q divided by pi d in the viscosity. Okay, if you use mass flow rate, m dot, the expression will be this. Since mass flow rate equal to rho times q, okay, so now in the denominator, nu become mu. Kinematic viscosity become dynamic viscosity. Okay, so Reynolds number, every pipe flow will have a Reynolds number. So most of the case, you need to calculate the Reynolds number. You need to tell people what the Reynolds number is, then people know what kind of flow is. Okay, based on the Reynolds number, we can determine if the pipe flow is laminar or turbulent. Look at this. Okay, for the pipe flow, if the Reynolds number is smaller than 2000, okay, we treat it as laminar pipe flow. If the Reynolds number is greater than 3000, we treat it as turbulent pipe flow. Okay, so both laminar and the turbulent pipe flow, we will have some equations to calculate the pipe, calculate the pipe characteristics. But the problem is between 2000 and 3000 Reynolds number. We call it transition region. Also, it's called unpredictable region. So in that region, the laminar flow model and turbulent flow model both doesn't work in that region. We create a lot of errors. So in that region, we don't have a clear, good model for that. So that's called unpredictable region. So usually we avoid the Reynolds number in that range. Okay, if you have to be that range, you have to do some measurement, okay, to understand the flow. But in the transition region, we don't have good models, okay? So now you use Reynolds number, you can determine if the flow is laminar or turbulent, okay? Again, Reynolds number is higher, that means the velocity is faster and or diameter is bigger, or you have less viscous fluid, right? Okay, let me introduce the pipe flow, fully developed pipe flow versus the developing pipe flow. Okay, this is the example of pipe flow. You have a pipe, you have an entrance. Okay, in the entrance, the velocity distribution is kind of like a uniform and rush into the pipe. So the velocity distribution inside the pipe actually changes along the flow direction. Look at this. At the beginning is a more flat this pattern, the distribution profiles. a little bit flatter, and gradually it become more parabolic. Okay, okay, but it gradually change, developing. Okay, but eventually to certain distance, the pipe, the flow no longer changing anymore. Look at this. After certain portion of the pipe, the flow becomes stable. Okay, and it doesn't change anymore along the x direction, along the flow direction. Okay, the profile becomes same. It doesn't mean the flow is uniform. No, it's not. But it doesn't change anymore. So that's called fully developed. Okay, so before you reach to fully developed flow, the region before that, we call it the developing region. Okay, so every pipe flow you will have a developing region. Okay, then eventually it will become fully developed. Okay, the length of the developing region, we call it entrance length. Entrance length. Okay, LE. In the entrance length, okay, all kind of flow model, it doesn't work also. Okay, it doesn't work either. Okay, just like a transition flow, right? Transition pipe flow. The model are for the fully developed regions. Okay, so in that sense, we don't have a good model in the entrance length in the developing region. So we probably at least need to know how long the entrance length is. Okay, so if we design a pipe, usually we want to have the pipe long enough, much longer than the entrance length. So most of the portion is fully developed. We have model. Okay, so we need to know how long the entrance length is. Okay, so there's a couple equations for entrance length. Okay, depending on if it's a laminar pipe flow or turbulent pipe flow. For the laminar pipe flow, the entrance length is 5% of Reynolds number times diameter. 0.05 times Reynolds number times the diameter of the pipe. That's the entrance length. For the turbulent pipe flow, it's a little bit simple. It's just 50D, 50 times the diameter. Okay, that's the developing region in the entrance length. So in other words, if it's turbulent pipe flow, the entrance length is kind of constant. Okay, it's just 50 times the diameter. It's nothing to do with, it's not a function of Reynolds number. But for the laminar flow, even you have a same pipe, same size of pipe, the entrance length changes with Reynolds number. If you have a different fluid there, if you have faster or slow flow there, the entrance length will be different. But for the turbulent pipe flow, if it's turbulent, hey, it's nothing to do with Reynolds number. Okay, it's basically the size, 50 times the diameter. Okay. The other thing I want to mention is the shear stress, wall shear stress distribution along the pipe. So the shear stress is important to know in the pipe flow because that's the friction, right? Okay, so it tells you here the shear stress along the pipe wall become constant in the fully developed region. It doesn't change anymore because the flow doesn't change, right? You remember shear stress is viscosity times du dy. So if the du dy become constant, your shear stress become constant. It doesn't change anymore, okay? But in the developing region, the shear stress decreases, okay? In the entrance, exactly in the inlet, you have a higher shear stress. It gradually decreases, then becomes constant in the fully developed region. Okay, this is some introduction of the pipe flow. Okay, in the pipe flow, the most important thing to characterize to quantify is the head loss. Okay, so if you design a pipe, you really need to know the head loss in the pipe. Okay, so we talk about the head loss a little bit in chapter 7, energy principles. Here, let's review it. The total head loss, there are two components contribute to the total head loss. The frictional head loss, HF, and the minor losses. Minor losses from the fittings, from the entrance, from the outlet, from all the components that connect to the pipe. Okay, everything contribute a little bit loss. We call these are the minor losses. Okay, HF is frictional head loss. If you have a pipe, basically that's a major loss, right? So that's related to the shear stress. We talked about it previously. Okay, so I put a summation here because you might have multiple pipe might change diameters in the systems and multiple pipes, and so there's summation. There's all multiple component and there are multiple components there. Okay, there are a lot of minor loss components. So we put a summations. Okay, so sometimes the calculation will be tedious, depending on how many components there, how many pipes in the pipe system. Okay. Okay, so let's separately talk about these two losses: frictional head loss and the minor losses. Frictional head loss first. HF, the Darcy-Weisbach equation. Okay, that's the major equations for you to calculate the frictional head loss. Okay, in this chapter, HF equals to F times L over D V squared over 2G. L is the length of the pipe. D is the diameter, right? V is the velocity. 2G, G is the gravitational acceleration. F is called friction factor. Okay, so you have a coefficients in this equation to be determined, right? The coefficient is friction factors. Okay, so next question is how do we determine the friction factors? Also, it depends on the laminar or turbulent pipe flow. Okay, if it's laminar pipe flow, we have an equation for F. If it's laminar, F equal to 64 over Reynolds number. Okay, 64 divided by Reynolds number. Okay, that's easy, right? If it's laminar, so you really want to calculate the Reynolds number for all the pipe flow first, every pipe flow. So if it's laminar, your friction factor is just 64 divided by Reynolds number. Okay, but if it's turbulent pipe flow, okay, so we don't have a analytical solution, like a theoretical solution, like a 64 over Reynolds number, like that. So everything is empirical, and we have correlations. Okay, we measured it before use experiment. So we conclude all those correlation into a diagram called Moody diagram, very famous Moody diagram, right? Okay, so in that diagram, use that diagram, we can find our F friction factor for the turbulent pipe flow. Okay, so Moody diagram, there's also a correlation equation 10.39 in the textbook you can use. It's same as the Moody diagram. Basically, that's the correlation from the Moody diagram. Okay, it's up to you, but usually we use Moody diagrams. That equation is pretty difficult to calculate. Okay, Moody diagram is in the textbook, figure 10.14. Okay, and on the page 374 to 375. Okay. To use Moody diagram, we need to have a couple informations. Okay, surface roughness of the pipe. So that's a property of the pipe. We can find it from the table 10.4 listed the surface roughness. Of course, we need a Reynolds number, right? You can calculate the Reynolds number. Then also a value in the top axis. I will show you in a second. Okay. So next, I will show you how to use Moody diagram to find F. Okay, this is the Moody diagram, figure 10.14 in page 374. Okay, this is a diagram. So look at it, it's pretty complicated, right? The bottom axis is the Reynolds number. Okay, so the left axis is the friction factor F. So that's the goal, right? Left axis. Okay, you have many curves in there. Okay, the right axis is surface roughness. It's relative surface roughness. Say K is the surface roughness divided by D, diameter. So that's the roughness relative to the diameter. Okay, so you need to find the surface roughness. It is in the table 10.4. So for different material, piping materials, it gives you the K value, okay? K value in terms of millimeter and or in terms of inches, okay? So that conclude summarize most of the materials, piping materials. So use this table 10.4, you should be able to find your K. Okay, then divided by diameter, right? Divided by diameter, that's your right axis, relative roughness. Okay, so if you have a Reynolds number, if you have a surface roughness, and then you can, based on the roughness, surface roughness, you can pick a curve here. There are so many curves, each curve representing a roughness. Okay, so for example, if your surface roughness is a relative surface roughness is 0.0002, okay, so that's a curve you will look at. Okay, so based on that curve, you have a Reynolds number down here, right? If my Reynolds number is 10 to the 6, okay, so on this curve, I located 10 to the 6 Reynolds number. Okay, then extend it to the left axis. It gives you the friction factor F. Okay, you pick a curve based on the roughness. Okay, then find your Reynolds number. Okay, then you should be able to find your F value. Okay, that's the bottom axis Reynolds number and the right axis. Based on this, use these two axes. To these two values, you should be able to find your F. Okay, there's another option here. If you don't have Reynolds number for some of the case, if you have a roughness, if you have the top axis value, okay, there's a complicated expression here. But in this expression, you don't need a velocity, right? Look at this, right-hand side of the equation. If you don't have velocity, sometimes, for Reynolds number, you need a velocity, right? If you don't have velocity, you cannot calculate the Reynolds number. But with this expression, you don't have velocity, but if you have the loss, the value of the loss, then you can use the top axis along with the right axis, relative roughness, to find your Reynolds number, or to find your friction factor. Okay? So that's an option. Okay. You pick a curve, the blue lines, right? Pick a curve based on the roughness, then find the top axis value. Okay, then you can find the friction factor F. So either you can use bottom axis or you can use top axis based on what you have. Okay, for the front problem. Okay, this is how how to use the Moody diagram. Very important. Okay, most of the problem in this chapter, you need to use Moody diagram to find the friction factor.